In this session, we will have a brief introduction of speech separation problem, which is often called cocktail party problem. Speech separation is the general task of separating targeted speech from background interference, which may include non-speech noise, interfering speech, or both, as well as reverberation. In real applications, human voice is transmitted to the recorder by air prognation or channel. During the transmission, channel distortion, active noise from other sound sources, and reverberation from surface reflections make the recorded speech noisy and degraded. If we want to hear the voice clearly, speech enhancement and speech separation techniques are needed. Speech separation is commonly called the cocktail party problem, a term coined by Jerry in his famous paper in 1953. One of our most important faculties is our ability to listen to and follow one speaker in the presence of others. This is such a common experience that we may take it for granted. We may call it the cocktail party problem. No machine has been constructed to do just that. For cocktail party-like situations, when all voices are equally loud, speech remains intelligible for normal hearing listeners, even when there are as many as 6 interfering talkers. In the history, Helmholtz proposed the ballroom problem, which described the complicated beyond conception. CASA, Computational Auditory Scene Analysis, defines the solution to the cocktail party problem as a system that achieves human separation performance in all listening conditions. We can use speech reception threshold, SRT, to quantify the speech perception performance. Miller reviewed human intelligibility scores when interfered by a variety of tones, broadband noises, and other voices. Listeners were tested for their word intelligibility scores, and the results are shown in the figure. In general, tones are not as interfering as broadband noises. Speech is intelligible even when mixed with a complex tone. Broadband noise is the most interfering for speech perception, and the corresponding SRT is about 2 dB. When interference consists of other voices, the SRT depends on how many interfering talkers are present. There is a big SRT gap of 23 dB for different kinds of interference. Given the importance, speech separation has been extensively studied in signal processing for decades. The researchers in the field of speech separation could be speech enhancement, that is speech non-speech separation, speaker separation, that is multi-talker separation, and speech dereverberation. As to speech enhancement or denoising, we mainly mean the separation of speech and non-speech noise. If one is limited to the separation of multiple voices, we use the term speaker separation. There are many techniques to solve speech separation problem. Traditional monaural speech enhancement mainly to realize denoising. Multi-microphone techniques indeed use traditional approaches to solve separation based on spatial information, including beamforming. Time frequency (TF) masking in CASA, computational auditory scene analysis, applies a two-dimensional mask weighting to the time frequency representation of a source mixture in order to separate the target source. A more recent approach treats speech separation as a supervised learning problem with deep learning techniques, which mainly contains three questions: learning machines, training targets, and acoustic features. A major goal of CSA is the ideal binaural mask, IBM, which denotes whether the target signal dominates a TF unit in the time frequency representation of a mixed signal. IBM is motivated by the auditory masking phenomenon and auditory scene analysis. The basic idea is to retain parts of a mixture where the target sound is stronger than the acoustic background and discard the rest. Listening studies show that ideal binaural masking dramatically improves speech intelligibility for normal hearing and hearing impaired listeners in noisy conditions. There is an example to illustrate IBM-based speech separation. The target speech is a male voice.
Primitive tribes have an upbeat attitude.
The intrusion sound is a female voice, which interferes the male voice.
Only the best players enjoy popularity.
This leads to a mixture sound with two voices that human cannot distinguish the speaking content easily.
Only the best players enjoy popularity.
Attitude.
Using IBM to do the separation, a masked mixture can be obtained which has a high indability.
Primitive tribes have an upbeat attitude.
According to the subjective test, IBM separation leads to dramatic speech intelligibility improvements. Improvement for stationary noise is above 7 dB for normal hearing listeners and above 9 dB for hearing impaired listeners. Improvement for modulated noise is significantly larger than for stationary noise. With the IBM as the goal, the speech separation problem becomes a binaural classification problem. This new formulation opens the problem to a variety of pattern classification methods. In speech separation, there is a special task to solve multi-speaker or multi-talker problem, which mixes interference speech into the target speech. There is an example to show the mixed sound, including several speakers, which is confusing when listening.
Bin blue at D5 now. Bin blue at D5 now.
Bin blue F2 now.
Bin blue at B8 now.
It belongs to the problem of blind source separation, which is to separate one speech source from another. Unlike speech enhancement, speaker separation aims to extract the target speaker from a multi-talker mixture. There are some evaluation objective metrics commonly used in speech separation. These metrics can be divided into two classes: signal level and perception level. At signal level, matrices aim to quantify the degrees of signal enhancement or interference reduction. In addition to the traditional SNR, speech distortion loss and noise residue in a separated signal can be individually measured. A prominent set of evaluation metrics comprises SDR, source to distortion ratio, SIR, source to interference ratio, and SAR, source to artifact ratio. As the output of a speech separation system is often consumed by the human listener, a lot of effort has been made to quantitatively predict how the listener perceives a separated signal. Because intelligibility and quality are two primary but different aspects of speech perception, objective metrics have been developed to separately evaluate speech intelligibility and speech quality. In recent years, the most commonly used intelligibility metric is STOI, short-time objective intelligibility, which measures the correlation between the short-term temporal envelopes of a reference, clean utterance, and a separated utterance. The value range of STOI is typically between 0 and 1, which can be interpreted as percent correct. For speech quality, PSQ, Perceptual Evaluation of Speech Quality, is the standard metric and recommended by the International Telecommunication Union, ITU. PSQ applies an auditory transform to produce a loudness spectrum and compares the loudness spectrum of a clean reference signal and a separated signal to produce a score in a range of minus 0.5 to 4.5, corresponding to the prediction of the perceptual MOS, mean opinion score. That's all for this session. See you next session.